Hello. Number 6, refraction. Now we've dealt with refraction before when we were looking at sound and waves in general speaking, and so in some ways this will be a recap, but we're going to go into a little bit more detail in terms of light. So refraction is the bending of light rays at the boundary or interface as they go from one medium to another. And this is an example. Here we've got some vertical blinds and we've got a wine glass, and the vertical blinds are straight, but the light here, because it's going through a lens, is getting bent and we're not seeing exactly the same images behind it. And here we have another example. Light is being refracted by a lens, and here the straw goes into water, and we've probably all seen this where it looks like the straw is bent, and therefore the light is being we're getting an optical illusion due to the light refracting at the various interfaces, and so but doesn't stop us having a drink with a straw. This is another example, very good example, in that this is the effect of swimming goggles or scuba diving goggles. The human eye is pretty much evolved to work in air, and when it works in air, everything is works pretty well and everything focuses at the right point. Now when we dive into water and open our eyes and try and look at things, the focus point is way behind the eye, and so everything looks blurry and doesn't look, we can't see underwater. Unlike some animals that have evolved, animals that continuously live underwater have evolved so that they can open their eyes and see clearly underwater, whereas other animals that go, like seals for example, they've evolved mechanisms that allow them to see perfectly well under the water. Some of them have a secondary lens that goes across their eye, but there's other mechanisms as well. Now for us humans though, we can't evolve that rapidly, therefore we need to wear goggles if we want to see underwater. And what the goggle does is, because the human eye is designed to work in air, and we use a glass plate, because we have air there, the refraction is such that we can see perfectly clearly underwater when we wear goggles. Now here's a light beam going through a prism and it's being refracted, and we've seen that, we've demonstrated that, and so let's have a look at it a bit more. Now what's happened there, we need to push this one back. I'll just fix that in a sec. Come on. Alright. 1, 2, 3. So here we've seen refraction. We've seen this with a light box. And we also see it when stars at night. They twinkle because of the refraction that's occurring due to the Earth's atmosphere. If you jumped up onto the moon where there's no atmosphere and looked at the stars, they wouldn't twinkle, they'd just be spots of light, which would be interesting to see. So just now we're going to just do a few definitions. Here's our incident ray. This would be our angle of incidence. This is our interface. This is the normal to the interface. The normal is what we take our angles from. A lot of students want to use this angle here, especially if they're given this angle here. They've got to do the angle to the normal. And this would be the angle of refraction. This is the path of the undeviated ray, and then the ray comes down here. We treat this as a separate interface. Just happens that these two are parallel. Therefore we've got an angle of incidence and an angle of refraction again. We've done that before, and this is out of our textbook. Now this book uses I as the angle we would normally use. Let's get a color here. I would recommend, or our information sheet uses theta I as the angle of incidence, and then we use theta R as the angle of refraction. And you might put, and this is from air to glass, and so this whole interface we consider different from this interface here. And so if we were to analyze this, this would now become your angle of incidence, and this is your angle of refraction. And when we look at these and analyze these using Snell's law, which is just about to come up, we treat them as separate. Alright, let's move away. So now, before we do that, we need to know a measure of what's called the optical density, and this is the ability of materials to have light pass through them. And the optical density equates to the velocity that the light actually travels through the material. So optically dense materials, for example diamond and glass, the light travels very slowly through them, and therefore has a greater effect on them. Whereas less dense materials, the speed of light is pretty close to that of a vacuum. So something like air would be optically less dense than diamond and glass. Another dense material we commonly use is water and ice as well. So light rays bend towards the normal when they go from a less dense medium to a more optically dense medium. So let's just say that again. Light rays bend towards the normal when they go from a less optically dense medium to a more optically dense medium. They bend away from the normal when they go from more optically dense to less optically dense. So in our previous example, if we were going, let's draw this, what colour am I? That should do. If we're going from, let's pick another colour. If we're going from air to water, okay, the light ray comes in, this is our normal, so the V air, the velocity air, is much greater than the velocity of light in water, water, let's correct that, and therefore the beam, if that's the continued path, it's going to bend towards the normal. Let's go with green, here we go, and so it's going to go in that pathway. So that would be our angle of incidence, and that would be our angle of refraction, and our angle of incidence is going to be greater than our angle of refraction because we're going from less optically dense to more optically dense. So we're bent towards the normal. What that means is the angle here is reduced. If we do the converse, let's see if I can do that. Let's draw our boundary again. Let's go from water to air, and where's our, let's go blue. This is our light, there's our normal, okay, and this would be our angle of incidence. Now this is more dense, this is less dense, so it's going to bend away from the normal. So if that's the path that it would have gone, it is now going to go away from the normal like that, and this will be our angle of refraction. And conversely, here we said the angle of incidence is now smaller than our angle of refraction, and that's what's meant by bending away from the normal. And we'll do lots of examples of those, so you'll get your head around that. Now, the absolute refractive index is another term we need to introduce, and it's the ratio of the velocity of light in air, or strictly speaking a vacuum, to the velocity of light in a different medium, glass or water, etc. And it's a constant for that medium, so every different medium has its own absolute refractive index. And this is how it's calculated. VA, so that would be air. I would like to write air, and V medium, and N is the letter we use. Okay, so every substance has its own unique absolute refractive index. Velocity in air, velocity in medium, absolute refractive index. Do not confuse this with the relative refractive index. Now, the relative refractive index is something that we calculate for every interface, and so that's different from the absolute refractive index, which is always relative to air. Now, we use the absolute refractive indices to calculate the relative refractive indices, and we'll get to that shortly. So there's another diagram showing that again, and we've got that again. Now here again we can see what we're trying to show here is that we're going from air to glass, so it's being bent towards the normal, and here it's being bent away from the normal. And we'll look at the light boxes and we'll be able to do those questions. And in the next video we're actually going to look at Snell's law, and that's a good point to stop. See ya.